Now, the Schrödinger equation heavily relies upon this very abstract concept known as the wave function. And the wave function is a key component into understanding all of the dynamics and specified properties of a particle or a system of particles that you would almost always want to know if you were to describe it and illustrate what is going on at a quantum level. So that is what we're going to be deriving today. Now, before I begin, I want to give a little bit of a backstory into the events leading up to the Schrödinger equation's inception. And the events really just begin around 1900, where Max Planck takes the initiative to resolve an ongoing conflict in physics known as the ultraviolet catastrophe. And the ultraviolet catastrophe has a lot to do with what is known as a black body and trying to map out its radiating spectrum as a function of temperature. So the more temperature you apply, the higher and higher the frequencies become. So you start out with longer wavelengths and it starts to gradually re-emit higher and higher frequencies. And the problem was within the framework we were using, once you got into the ultraviolet range, then you would see the frequencies shoot up to infinity. And this was not okay. This was unacceptable within a theoretical framework to have this blatant inconsistency. So what Max Planck did when describing the heat radiation of an electric resonator, what he looked at least from a classical standpoint, was that these resonators obeyed a continuous spectrum. An ordinary classical resonator had a continuous spectrum that was accepted and internalized amongst many of the community. But what Max Planck did was incredibly bold. He quantized that energy, and that was a very controversial idea at first. But ultimately, it resolved the ultraviolet catastrophe. There weren't any infinities popping up in the equations, and that more or less settled the ultraviolet catastrophe by virtue of this quantization of energy. Now, come around 1905, we have Albert Einstein. And Albert Einstein gave rise to what was known as the photoelectric effect. And what he was attempting to do was describe particles using an equation that Max Planck gave us. And the equation he gave us was this one right here. E equals hf. And what Einstein wanted to do was show that particles, or light rather, behaves in terms of particles. It is a little corpuscle, effectively. And for many generations, people were under the belief that light was a wave. What Einstein ultimately ended up doing was looking at how high-frequency light interacted with ordinary gases. And what he saw is that the interactions behaved according to the laws which govern these ordinary gases. So to verify this particle theory of light, what he did was reverse engineer those laws to prove that there was a heavy dependence upon there being spatially localized lumps of matter in these particular systems. And by virtue of these spatially localized lumps of matter, that led to Einstein coining the phrase quanta, which effectively just means a little bundle of light, a little bundle of energy, rather. Now, following Einstein, we have Niels Bohr, who comes around in 1913. And Niels Bohr, once again, took a lot of these ideas and he had to reconfigure them because at the time, people were under the guise of the nuclear model presented by Ernest Rutherford. And Rutherford gave us a very good picture. He allowed us to see that the atom was mostly empty space, where most of the mass was contained in a single point called the nucleus because of his alpha particle experiment. Now, the problem that we saw within that particular framework was that in describing these electrons orbiting around the nucleus like that of a system, a planetary system, what we saw is that this ended up being a little bit problematic due to the fact that there was nothing restricting the electrons from spiraling into the nucleus and crashing into it. So what Niels Bohr did, he comes around and asserts that these electrons are stationary in their orbits around the nucleus. They are implanted and occupy stationary orbits around the nucleus. And whenever an energetic quanta of light collides with one of these electrons in their stationary system here, well, what would end up happening is that the electron would absorb the photon, or the quanta of light, that would obviously be equivalent to whatever this is, and is dependent upon the frequency to cause the interaction to create an excited electron. And what that would do was shift the electron towards a higher state, and over some duration of time, it would traverse backwards and try to reach its ground state, and then re-emit a photon in the process. Okay? So, that was a very compelling resolution to some of these conflicts. And to verify some of these ideas, what Niels Bohr did was quantized angular momentum. And to quantize angular momentum allowed him to summarize where these electrons should be occupied around the nucleus. And this was also very compelling, even though he kind of pulled it out of thin air to some extent, but it satisfied a lot of the requirements that we needed to sort of fix and reconfigure some of the problems within the model of Rutherford's model. Now, what are the problems with the Bohr's model? Well, the problem with the Bohr's model is that it violates the Heisenberg uncertainty principle. It doesn't work well in multi-electron systems. It works well in hydrogen and helium, but when you extend it to higher electron systems, it just kind of falls apart. And then additionally, the problem being that it is a 2D representation of an atom. And we know that atom and matter in reality is three-dimensional. So something needed to change. And lo and behold, we have some of the revolutionary figures come around between 1920 and 1925, where we have Max Born, we have Louis de Broglie, and we have Werner Heisenberg. In that particular timeline, Werner Heisenberg and Max Born invented the first quantum mechanical formalism known as matrix mechanics, which is kind of a special case of Schrödinger's wave mechanics, but it's more or less an accurate depiction of how quantum mechanics works, and it leads to the right kinds of predictions and phenomena that you would expect. I see more often than not, people tend to lean upon the Schrödinger equation or just his wave mechanics in general. That seems to be a little easier to come to terms with, develop some intuition for. Now, when Louis de Broglie came around, he postulated that the electron does in fact have a wave associated with it, because at the time people were still grappling with the idea that how could the photon be a particle and a wave at the same time? Well, the one thing that popped into Louis de Broglie's head was that why not the electron too? Because clearly, dependent upon the experiment being performed, the photons behave differently depending on whether you are doing a photoelectric effect where you're bombarding a piece of metal with photons and trying to eject electrons, or you're shooting it through a double slit. Well, you're going to get a different result depending on how it's orchestrated. So why not the electron? And what Louis de Broglie said was that the electron has a wavelength similar to that of light. Okay, so what he did was he showed that this equation for the electron was true, h over p. So we have the wavelength equal to Planck's constant over the momentum. And this was verified later in experiment, similar to how the wave-like properties of light was uncovered through a diffraction experiment, through a double slit experiment with a very, very small slit because the electron's wavelength is incredibly tiny, but we got an interference pattern verifying that the electron does in fact have a wave-like property. So great. Now, this lays the groundwork very nicely for Schrödinger to take over and extend Louis de Broglie's ideas and adapt to this new sort of paradigm by creating his eponymous equation, or his eponymous partial differential equation. So with that in mind, let's start describing the wave function. Before we start getting into the Schrödinger equation, I want to quickly run down what the wave function is and how we can represent it quantitatively before I start deriving the Schrödinger equation. So let's get it. All right, so first, the wave function. Let's start describing that here. All right, so the wave function, before I just start telling you what it is, I'm going to show you what it is first. So the wave function is represented by the Greek letter psi, and that is a function of x and t, and it is equal to Euler's number E raised to I times kx minus omega t. All right, so in my personal experience, just looking at this does not give me enough information to know, at least immediately that is, whether I'm actually dealing with a wave. How is this describing a wave? But first, before I get to that, I see probably, or noticing this I here, this imaginary I. Now, for those who don't know, I will quickly tell you what I represents. So I is equal to the square root of -1, okay? And similarly, I squared is equal to -1, right? Well, if we wanted to apply this in a more sort of generalized sort of setup, well, if we were to take a squared equals minus b squared, well, immediately, if we weren't applying the imaginary numbers, or what is also referred to as the complex plane, well, this would have no solutions. We wouldn't be able to do anything with this. But if we are to employ the imaginary numbers, then what we end up with is a is equal to plus or minus bi. Okay? So, and if you're wondering, the plus or minus, these are just conjugate pairs, and that is just the technical terminology to describe what that is. It's entirely that important for our purposes here, but in case you wanted to know, there you go. So, next, let's start breaking down why this is a wave, okay? So, to do that, and you might be wondering, how does this I even contribute into the description of a wave in general? Now, you're not going to find a whole lot of satisfying answers for this, but to put it lightly, this I, the complex plane, is incredibly useful mathematically. It is a mathematical tool. It's very good at describing 90-degree rotations. So hopefully that at least gives you a little bit of ease, knowing that it's not just some arbitrary thing that we're throwing in here. But with that in mind, let's actually start showing you that there is in fact wave-like properties associated with this quantity here. So first, I'm going to take out the imaginary part here, I and k and x, okay? So we're going to have e raised to the I kx. Now, if you've seen any of my previous videos, I derived what was known as Euler's identity, and that is incredibly useful when trying to describe this particular quantity here. Because, according to Euler's identity, and if you want to actually watch it, I'll leave the link in the description below, but furthermore, we have e raised to the I kx will be equal to cosine of kx plus I times sine of kx. Okay? So this at least helps me tether a little bit of intuition as to how this could possibly be a wave, because obviously this cosine and this sine, these trig functions, describe waves in and of themselves, okay? So let's look at this cosine factor here. So for cosine of kx, we can write out, or we can actually describe it on a little bit of a graph here. So if we were to write out a graph and create some y-axis that had a maximum value of +1 and a minimum value of -1. Well, because cosine is symmetric about the y-axis, we're going to start here. Because at cosine of 0, we have 1. So if we were to write that out here, we're going to keep going. All right, so first, obviously, this is our origin point at 0. And as we move down towards the x-axis here, which I'm calling the x-axis, of course. And this particular value will be, of course, pi over 2, because cosine of pi over 2 is 0. And then as we go down further to this peak, we have pi, cosine of pi. And then back up again, we're at cosine of 3 pi over 2. And then back up here, we have 2 pi. Okay? So that is how we can represent our cosine function here. And the distance between peaks here is known as the wavelength. So what we are describing here is what is known as a standing wave. And this is a standing wave because it just oscillates in space through time, but it doesn't move anywhere. It just oscillates about the x-axis. So it just goes between both amplitudes, which are +1 and -1. Okay? So for cosine, if we were to sort of represent this argument here, we'd have to know what k is, of course. And k is the wave number. K is equal to 2 pi over lambda. Okay? And assuming that x is equal to lambda, well, then we just have cosine of 2 pi, which is equal to 1, as we see here. So that's all good and good. So that's great. So now what we want to do is extend this to what we see here in this part of the argument, this omega t factor. So if we were to, once again, take our cosine and replace the argument with kx minus omega t, well, now we have a little bit of a different sort of representation of this wave, and you'll see why. So if we were to say, establish a little bit of a boundary condition where cosine is equal to 0, what do we have? We have kx minus omega t equals 0. If we were to move that over, we got kx equals omega t. And rearranging a little bit, we have x over t is equal to omega over k. All right, so this, we have a position per unit time, which is nothing more than just the velocity here. That must mean this has to be velocity as well, but I haven't told you what omega is yet. And omega is what's known as the angular frequency. And the angular frequency is equal to 2 pi times the linear frequency. Okay? So if we plug these in, what we get, we plug k and omega in, what we end up with is the frequency times lambda. And lo and behold, frequency times lambda, if you do some dimensional analysis, that is, of course, equal to velocity. So now, this is what this is describing is the wave now moving through space, as opposed to about its x-axis here as a standing wave. So now we have our wave moving with some arbitrary velocity v here. Okay? So I hope this gives a little bit of grounding and establishes a little bit of intuition for what the wave function is, and will hopefully make it a little bit easier to sort of understand some of the concepts that come out of the Schrödinger equation, especially in some of my later videos I'm going to be making. So for that matter, let's actually get into the nitty-gritty. Let's derive the Schrödinger equation, and I'll see you there. All right, so let's start deriving the Schrödinger equation. So before we begin, let's reach into our classical grab bag of energy conservation, and that is what we're going to be laying to at least build our partial differential equation around, okay? Now, the fact that we're using classical energy conservation tells you that there is kind of an issue. There's an issue due to the fact that we can't use the Schrödinger equation to describe relativity or the quantum mechanical spin of a particle. It just doesn't work. It is because the Schrödinger equation is not invariant upon Lorentz transformations. And that, for that, you need the Dirac equation, which maybe someday I'll derive, but I'm not currently at that level, unfortunately. But for that matter, Schrödinger equation Still pretty novel, describes a lot of things, did a lot for physics and chemistry. So first, let's take our energy, our total energy of our system, which is equal to the kinetic plus the potential. So we're going to have E equals P squared, which is the momentum, over 2m, plus what we're going to represent. I think this is a capital nu. I'm not entirely sure. It's a V, but it's also a Greek letter. So we have that being the potential as a function of position. All right, so this is going to be our basis. We're going to be referencing this shortly. But first, what we want to do is take some partial derivatives of our wave function with respect to position. So first, we'll take our partial of psi as a function of x and t with respect to the position. Well, what does that give us? Well, that is just simply equal to, well, this x is going to be 1, and since we're bringing it down, we just have ik. And obviously minus omega is just our constant here, so that there's no need to concern ourselves with that. So ik times e raised to the I times kx minus omega t. All right? So now what we can do is take another derivative. And what you'll be noticing here is that this will never change. This wave function portion of our new value is always going to be left within the equation. And that is because it is referred to as an eigenfunction. And the factor that it's being scaled up by is known as the eigenvalue. Okay? Now, this tends to be a little bit more abstract, especially if you've had any formal training into what eigenvalues are, and eigenvectors for that matter. And I can definitely make a video on that at some other point, but all you need to know is that we are trying to describe the eigenstate of a system. That is the ultimate goal when trying to solve the Schrödinger equation. But this becomes incredibly important because it doesn't change, especially when you differentiate it. So let's differentiate it again. We're going to have d psi of x and t. So that's going to be squared. Dx squared is equal to ik squared. And then because we have our eigenfunction, that is just going to be left right there. Okay? Great. So now we need to define a new value of k. We know already that k is equal to 2 pi over lambda. Well, what other sort of terms are we going to need for this derivation? Well, I'm going to write a few down because they're going to be very key into the derivation that we're performing here. So we have k equal to 2 pi in lambda, and then we have our angular frequency, which is equal to 2 pi times our frequency, our linear frequency. And we need Louis de Broglie's equation, which describes the momentum of a particle. So we have P, which is equal to h, or Planck's constant, over lambda. And similarly, we can obviously write the wavelength is h over p. Okay? Now, we can also take Planck's equation that we have just introduced, because that is also going to be very useful later on, where we have E, which is equal to Planck's constant times the frequency, which can be rewritten as E equal to h bar times omega. And h bar is equal to Planck's constant over 2 pi. And if you'll plug in some of these quantities, you'll see that they cancel, and you just end back up with what we started with, E equals Planck's constant times the frequency. Now, we can also describe the momentum similarly, where we have P is equal to h bar times k, where once again, if you plug in h bar and k, these two pi's will cancel, and you're just left with your good old de Broglie equation again, your momentum. Okay, so that is what we're going to be using for this purpose. This equation right here. So what we have is now K equals P over H bar. Okay? So we can plug that in here now. And what we get is that since I squared, as we showed, is just equal to -1, we're going to have minus P squared over H bar squared times the wave function of x and t. All right, so we want to take this negative and this h bar squared and bring it over to our partial, which gives us minus h bar squared times our second partial derivative of the wave function with respect to position over that. Okay, now that is going to be equal to momentum squared times our wave function. All right, and as I mentioned before, we are going to be using our total energy here, and what we're going to do is multiply our energy by our wave function. So what that gives us is E times our wave function of x and t, is equal to, now p squared over 2m, right? Times our wave function of x and t, and that is going to be added to our potential, function of x and t. Okay, cool. So now what we can do is actually plug this little boy in here. That's right, it's a boy. Now this is going to be plugged into this portion of the equation right here because we have p squared and our wave function. So that can be replaced and substituted. And what we have is E times our wave function of x and t is equal to negative h bar squared over 2m times our partial squared function of x and t over dx squared plus our potential function of x and our wave function here. Now what we have here is our first piece of the Schrödinger equation. This is what's known as the time-independent Schrödinger equation. And this is useful in a lot of different ways as well. This is going to be actually the focus of my next video, and I'm going to be solving it for a particle in a box. So this will be something that I use later, but we can do better. We can actually bring out the time-dependent Schrödinger equation. So let's segment this off, and we now know that we have the time-independent Schrödinger equation. Okay, now I'm sure you may have guessed at this point, to find the time-dependent, well, we need to differentiate with respect to time now. So let's do that. So we're going to have d psi, function of x and t, with respect to time, which is equal to, now what that gives us is minus omega. Okay, so minus I omega, I should say. Minus I times omega times our wave function, x and t. Okay, so now we want to do something similar where we multiplied our wave function by the energy, but this time we are going to use the revised Planck relationship here, because now we're dealing with an omega term. We can easily sort of manipulate this such that we can now substitute it, hopefully, into the time-independent Schrödinger equation. So now let's multiply our wave function by our energy. So once again, E times our wave function of x and t will now give us h bar omega times our wave function of x and t. Okay, so great. Now, how can we work with this? Well, what I like to do, there's another number of ways you can do this. I like to just bring this negative I over to the other side and then make the substitution. So we're going to have minus 1 over I times our partial t over dt is equal to omega times the wave function, but we can actually substitute, well, we will actually substitute into this equation. So what we get, of course, is just omega times our wave function s and t. Excuse me. So now we just want to plug this in right here. So what we get is now e times our wave function, x and t, is equal to negative h bar over I. So negative h bar over I. Technically, it's the I that's negative. You'll see what I'm going to do with that. So that is going to be also times our partial function of x and t with respect to t. Great. So what we can do is bring this negative I up and make it positive, by bringing it up to the numerator, and then substituting this entire equation back into our time-independent equation. And what we get is our new equation, I times h bar, with our partial, our wave function with respect to time, is equal to minus h bar squared over 2m. We have our partial x and t squared dx squared, and that is going to be plus, running out of room here, x. Got it. All right, and there we have it. This is the time-dependent Schrödinger equation. Time-dependent Schrödinger equation. Now, this is, I think, a very intuitive way of deriving the Schrödinger equation. There is other ways of doing it, which I may do in the future, and that requires knowing how operators work. And you can take this by using the momentum operator and sort of manipulating some variables and getting a similar result. Actually, the exact result, not just a similar result. You will get the exact same result. And that tends to be a little bit more consistent because operators are so incredibly useful and prevalent in quantum mechanics. But for our purposes here, I thought that this would be a nice little demonstration to get us started, because in the future, I'm going to be solving the Schrödinger equation, at least for my next video, where I'm going to be taking the time-independent Schrödinger equation, solving it for a particle in a box, and we will see that eventually this will start to evolve, and we will move up to harder and more difficult kinds of equations. And this is not the three-dimensional. Of course, this describes a one-dimensional Schrödinger equation, and the three-dimensional, as you could probably guess, is a lot more complicated, and that requires the use of the Laplacian. But eventually we'll get there, but this at least establishes the groundwork, and I hope you enjoyed it. Please like, favorite, and subscribe if you want to see more videos like this in the future, and thanks for watching.